So everyone, welcome back to this lecture. Today I will try to complete OPAM. We will end with this basic integrator and some uh, exercise, some conceptual exercise problem. And you for your continuous assessment test that will be held next week, the my portion for such test will be till today's lecture. So with this, we complete OPM and we have some remaining topics, instrumentation and all in unit 3. And also in unit 4, we have other topics that we will have to discuss. All right. So basic integrated circuit is as shown here in the figure. Again, here you have to differentiate between what is alternating current source and DC current source. So as I explained yesterday, this is an alternating current source. Sorry, alternating current AC signal source, right? And usually, as I said yesterday, your AC current is denoted with small letter I here. I subscript I means this is the input current. Small letter I subscript F means this is the feedback current. So as usual, this is your op-amp IC741. Pin number 7 is connected to plus VCC. Pin number 4 connected to minus VCC, your DC power supply. And pin number 6 is your output. Pin number 2 is your inverting. Pin number 3 is non-inverting input. Again, in this basic integrator, non-inverting input is connected to ground. So this is the symbol for ground connection. So this is 0 volt, right? And the output voltage is measured at this point, pin number 6. The voltage at this point, the voltage measured at pin number 6 is called your output voltage. So it is measured with respect to ground. So with respect to ground, you are connecting, here you see that there is a ground connection via this load resistance. So the load resistance is connected from the output terminal, between the output terminal and the ground. So this gives you your load resistance, RL, right? And here the output signal is supplied back to the input via this feedback circuit. Here, the difference here is that in basic integrator, the feedback circuit now consists of your feedback capacitor CF. Now consists of feedback capacitor CF. All right. And here you have an input resistor RI. So as I discussed before, the voltage at pin number 2 inverting input is denoted as V2. The voltage at pin number 3 and inverting is denoted as V1. So because of this feedback here, feedback circuit, this op-amp has the ability to set the two voltages V1 and V2 to be exactly equal in order to prevent the output from going into saturation. This op-amp will eventually set itself such that the voltage at pin number 1, pin number 2, and pin number 3 are equal. And uh, here, as I mentioned here, this pin number 3 is connected to ground, means V1 is 0 volt, means your V2 is also again 0 volt. And also there is a very high input impedance of about 2 mega ohm here in IC741, and because of the current entering this pin number 2, let me call it I2, your current entering pin number 2 I2 will also be 0 again. So these are the property that I believe you should be familiar by now. Now again, applying Kirchhoff law at this point, at this junction, the current entering the junction and leaving the junction are equal according to Kirchhoff law. So I is equal to IF. This is the relation we have again. And what is II? II is the current passing through this resistance Ri. So the current passing through resistance Ri will be equal to the potential difference across the resistance. So on the left side, the potential you supply here is Vi, On the right hand side, the potential here is your V2. V2 is the voltage at this pin number 2. So at this point, the voltage is V2. So V2 upon your Ri. So this is something we already discussed while we discuss inverting configuration as well as differentiator. So here you find that your V2 is 0. So this is equal to Vi upon Ri. And your IF again, so like I explained before yesterday, so the instantaneous charge here, you see that we are connecting AC signal. That means the instantaneous charge across the capacitor is given by capacitance into potential difference across the capacitor. So potential difference across the capacitor is, on the left side you have V2, on the right side you have V0, V2 minus V0. Okay, so the current IF will now be dq. Instantaneous current will be rate of change of your instantaneous charge, dq upon dt, cf, differentiation of v2 minus v0 upon dt. So this is going to be feedback capacitor cf. V2 is 0, so that means there will be a minus of d of v0 upon dt. Okay. Now, if you apply this Kirchhoff relation, what you're going to get out of this two expression here is that you will find that this will be Vi upon Ri equal to minus of Cf dV0 upon dt. So your dV0 upon dt will be equal to minus of 1 upon Ri into Cf Vi. So your V0 output voltage will be minus of 1 upon, these are constant, resistance and capacitance, integration of your input current. So as you see here, finally the relation between output voltage and input voltage, or when you express output voltage in terms of input voltage, you will find that your output voltage is minus of 1 upon Ri into Cf into integration of your input signal, So you can consider a certain integration constant like this also, but never mind. So this gives you a circuit using operational amplifier that can perform integration of your voltage signal, that is supplied at the input terminal. It performs, or it gives out integration of the voltage signal that is supplied at the input signal. Okay, so this is how the circuit will operate. It will simply, like if you give certain voltage signal here, whatever voltage signal integrated, the output will be the integration of such input signal. Okay, now this is what one of the problem I thought we will discuss. Before we discuss this problem, there's something I would like to tell you about negative and positive slope and all. So I think by now everybody will understand that if I write something like this, suppose there is a function and let's say there is a certain x-axis, for example. Now if you have something like this, that is f value increases with increase in x. So the functional value increases with increase in the x variable here, the variable on the x-axis. Then in such case the slope is called positive slope. So that means like for a certain value of, like for example, if you increase your x value by this del x, so if you have a del x positive, then corresponding to increase in del x at this point, what is the f value? F value is here. Okay, now when you increase your x variable up to this point, at this point, what is the corresponding value of f? The corresponding value of f is here. So you see that with the increase of x in this direction, your f functional value also increase. Del f is also positive. Okay. Del f is also positive. Del x is also positive. So the slope here, del f upon del x, is positive. Okay. And I think everybody understand that if the differentiation of function f with respect to x at a certain point will be simply when you take your del x, del x, that is the incremental change in x value, to be very, very small. So if you consider del x, the incremental change in x value, to be approaching to be zero, then this del f upon del x, limit del x tending to zero, will give you differentiation of the function f at a certain point. Okay, differentiation of the function f at a certain point. Now, and if I have something like this, f x, suppose I have something like this. Here in this case, let's say your initial x value is here, and you increase your x value up to this point. Suppose you increase your x value up to this point. So corresponding to this point, your functional value is here. Corresponding to the new point, your functional value is there. So if you will find that with increase of x, that is change in x is positive, there will be a decrease of functional value. Del f is negative. So when del f is negative, when del x is positive, the ratio here, del f upon del x, which you call it slope, right? This ratio is now negative. Okay, this ratio is now negative. So such kind of slope, like the one shown here, it may be a straight line like this, or it may be something like this. Whenever you find that the functional value decreases with increase in x variable, then the slope of the slope in that region is negative. Here, when the functional value increases with increase in x variable, then the slope in that region is positive. So I think this is something which I would like to recap here. Now, so let me consider something like this, some kind of waveform like this. For example, suppose I have a waveform like this. Okay, so let's say your voltage signal is here. Input voltage signal is something like this. It is 0 here, and it increases to its maximum value here, Vi max. So this axis is your T. Just a minute, what is wrong? So if you look at this, suppose you differentiate this here, your function or your y-axis is your Vi, your independent variable is your x-axis, is your time t, let's say. Okay, so let's say you differentiate dvi upon dt. Suppose you differentiate this. This is, let's say, your time axis. So what will be the differentiation of your Vi, that is your function or the voltage here, with respect to time? Can anyone draw and on your piece of paper and respond to me. What kind of differentiation will this be? Suppose the input voltage signal waveform is something like this, triangular. Okay, this is triangular. So this is going from 0 to this point, and this is a straight line. Okay, this is a straight line, and here also is a straight line. Let me go back to what I was discussing here. So if I have something like this, suppose if I have something like this, okay, let's say this is a function, this is your x-axis. Here in this region, you will find that the slope is very steep. The slope is very steep. That is, with like a small change in x, there is a correspondingly large change in f. Okay. Now, in this region here, sorry, I think let me so let's say we have the same interval del x, the same length, the same width, interval width here del x. Now you will find that for such same interval width also, the corresponding change in the function del f here is quite small. Now the corresponding change in the function del f is quite small for this interval. For the same width of this interval here, over here, your del f is quite large. So if you have this kind of curvature like this, your slope, even though del f is positive with respect to del x positive, here also del f is positive, del f increases with respect to del x increase. So even though they in this region here and there you have a positive slope, but over here the slope is much smaller. If you take del f upon del x is in this region over here, because of small del f, for the same value of del x, the slope is quite small here. So the slope will change. The slope, as you see in this kind of curve, it changes, isn't it? But if you consider a straight line, something like this, over here, let's say you have a certain interval with del x. With this del x, what is the corresponding f? Change in f, del f, it may be something like this. If you consider another 2 points here, but the same width, the same interval width here, del x here, if you consider the same interval width, you will find that your del f over here and del f over here, they are exactly equal if you have a straight line like this. So the slope is constant for a straight line. That means if you take a differentiation df with respect to dx, you will find a constant value. Df upon dx will be constant. Differentiation of the function f with respect to x will be constant if you have a straight line. Df upon dx is a constant, a certain value, a certain constant, right? But if your straight line is something like this, if your straight line is something like this, if you consider del x here, the change in f is a little bit larger. If you consider the same thing here, the change in f is a little bit larger. So this del f and this del f, they are equal as long as you consider a straight line. But depending on the inclination of this straight line here, your differentiation df upon dx value will be larger or smaller. If you have a straight line like this also, your df upon dx will give you a certain constant value from this point to this point. So along this straight line, df upon dx will be constant. Along this straight line, df upon dx will be constant. But your df upon dx for this particular straight line will be greater than the df upon dx you obtained out of this straight line. Because out of this straight line, for del x, that corresponding del f is much smaller. So your df upon dx, even though it is constant from this point to this point, df upon dx in between this interval will be what is that? Much smaller than what you have for this straight line with a larger inclination. So now considering that, suppose you perform differentiation of this voltage dvi with respect to the time axis here, and this is your VI waveform. This is your VI waveform. So can you tell me what will be the waveform after this differentiation? Can you tell me what will be the waveform after this differentiation? Let's say we are considering a differentiator. Yesterday we discussed a differentiator. So you remember that in a differentiator, output voltage is minus of R, what is that? Yeah, RF CI dVi upon dt. So this was what we have. Let us consider a differentiator, and let's say you have a triangular wave like this as the input. What will be your output here? Can someone make a prediction?
So it will be a square wave.
That is very, I don't know, I cannot hear you. Is it Ananta? I cannot hear you. Am I audible?
Yes, sir. So
Ananta's voice
it might
is
be a square
hardly
wave.
audible to me.
So it might be a square wave.
Just a minute. I think my volume, I hope I'm audible because I have spoken a lot of things. So
Yes,
this
sir.
is the problem with having online class. Maybe I have muted my video audio. Yes, I hope there's no
So it
problem
might
with, there was no problem with my microphone, I guess. But yeah, my
no, sir.
volume was muted. My laptop volume was muted. Now I can hear you.
So it might be a square wave, sir.
Pardon?
So it might be a square wave.
Yeah, it will give a square wave, definitely. Right. So here, between this interval, like between this to this, you find that the slope here is a constant, isn't it? dvi upon dt will be constant. It will result in certain positive constant. But there is a minus sign here because the differentiator and the integrator, because we circuit, if you remember, the input is supplied to the inverting terminal, right? So because of that, output voltage is always minus of certain quantities multiplied with the input, right? So even though this side between this interval to this, it is a positive slope, isn't it? This is a positive slope because with the increase of t time, you have an increase in vi, so you have a positive slope. So positive slope means differentiation of dvi upon dt itself will be a certain positive constant. But because of this minus here, inverting property here, it will result in a certain negative, something like this, isn't it? Negative constant, negative constant. And at this point here, if you look at this point, this is the maxima. At this point, your voltage is something like a plateau. It's the tip of your triangular wave here. At this point, momentarily, at this particular point, at this particular time here, remember that the x-axis is your time axis. At this particular time, you are just a minute. Oh, hello, sir. Hello. Hello. Oh, ole class ka nei me ka PG ka nei zo ve le ka lo upload sin don ya. Oh, tha chu ka lo an le oh sir. So at this particular point, at this maxima here, before the slope reverses from positive slope to negative slope, this is a negative slope. Momentarily at this point, your VI will be constant, isn't it? So at this point, it will go back to zero, something like this. And from here to here, in this interval, you find that the slope is negative slope here. So when you perform differentiation here, you will have a certain negative constant, but because of the inverting property of this differentiator, it will result in a positive constant value here. So it's a square wave. Okay, positive constant value is a square wave. So here, the reason why I wanted to show you here is that if you feed a triangular wave like this, you will get a square wave like this, isn't it? So if you remember, a triangular wave, it may continue something like this. So between this interval, it is again negative slope, isn't it? It's a negative slope. With the increase of t, you are still having this. So sorry, yeah, with the increase of this, you are having increase of vi in the reverse direction. So it's going to give you like increase of vi in the reverse direction is going to give you certain positive constant, and then with this inversion in this interval, you will have a negative constant like this, and between this interval, you will have something like this again. So it's actually your no, wait a minute, sorry, I was not thinking properly. I was disturbed a little bit. So between this interval also, you find that the vi value is decreasing like this. So it's still a negative slope, and it will get a, what is that? You will get a inversion here because of this inverting configuration. So it will remain constant like this. It will remain constant like this throughout. And from this point onwards, you now have a positive slope. So you will have a constant values like that. All right. Okay. So having said that, let us look into what we have here. Trace the output waveform for the basic integrator circuit shown below. So integration, you know that if you differentiate differentiation and integration, they are kind of reciprocal in the sense, if you differentiate cosine wave, you have a minus of sine wave, minus of sine theta. Uh, if you integrate sine theta, it will result in minus of sine theta, it will result in cos theta, you know, right? So if you remember that, if this is your input signal here, if this is your input signal here, something like this, if this is your input signal here, what you are going to get in the output will be, see, this is a negative constant, so it will result in, if you remember what we have just discussed, it will result in a this straight line like this, and between this interval, it will result in this. Okay, so these are something which you should, I mean, the kind of wave you will be having at the output terminal and all, this is something which you should be able to predict from this integrator and differentiator circuit and all. Now, can you please walk out on this? Identify the circuit given below. So what kind of circuit is this? You are having the feedback connected via this inverting terminal, and here non-inverting terminal is grounded. Non-inverting terminal is grounded, and you are supplying DC voltage here. This is a 1 volt DC. You are supplying 1 volt DC to inverting input. So that means your circuit given here is your inverting amplifier. This is your inverting amplifier. Okay, so we have identified the circuit as an inverting amplifier. Determine the amount of output current. So what will be the output current now? Output current here, the current at this point is called your output current, I naught. Okay, I naught here is split into IL. This is your feedback current and your load current. Yeah, so your current relation here is I naught is equal to IF plus IL. I naught is equal to IF plus IL. Right. So in order to calculate I naught, the output current here, what you need to obtain first is you need to obtain your IF and your IL. Okay. So in order to obtain IL, what is IL? IL is the current across this load resistance. So V naught is equal to IL into load resistance 5 kilo ohm. So IL is equal to V naught upon 5 kilo ohm. So you need to have your V naught first. So how do you obtain V naught? We have identified this as an inverting amplifier. Inverting amplifier means the closed loop gain ACL, which is output voltage upon input voltage, is equal to minus of RF upon RI. So this was the closed loop gain of inverting amplifier. So RF, we know it's already given here as a 45 kilo ohm. RI is your 10 kilo ohm. So your V naught upon VI will be equal to minus of 45 kilo ohm upon 10 kilo ohm. So your V naught will be this division will result in minus of 4.5 into VI, that is 1 volt. So 4.5 minus of 4.5 volt. So your output voltage will be minus of 4.5 volt. So if you have this as your output voltage, from this you can calculate your load current IL. IL will be minus of 4.5 volt upon 5 kilo ohm. So 4.5 upon 5 will be 0.9, isn't it? 4.5 divided by 5 will be 0.9. So this is minus of 0.9. So there is a kilo ohm, 10 to the power minus 3 in new denominator. So if you raise to numerator, it will be 10 to the power, 10 to the power 3 in denominator. If you raise to numerator, it will be 10 to the power minus 3, right? Volt per ohm is ampere. So this will be minus of 0.9 milliampere. Okay, so here the minus sign simply indicates the direction of flow of current. So your output voltage V naught here, V naught, the voltage at this point is minus of 4.5 volt as obtained here, right? So because of this, the current may flow in this direction. So never mind, when you write the current relation here, you will find that here the current is entering, IL is entering this junction from this to this, and IF is also entering the junction from this to this. So this is the current direction only. Okay, so you can take it as a I naught will be a summation of 0.9 milliampere and IF. Now, what is IF? Here, as I said before, the voltage at this point is called V2, and this voltage at pin number 3 is connected to ground, means this is also set at 0. As I explained before, V2 is also 0. So your IF will be the current passing through this 45 kilo ohm. The current passing through this 45 kilo ohm will be potential difference across this 45 kilo ohm, that is V2 minus V naught upon the resistance. Okay, V2 minus V naught upon the resistance value. So your IF will be V2 minus V naught upon 45 kilo ohm. So V2 is 0. So your V naught is minus of 4.5 volt, 45 kilo ohm. So this will be 4.5 divided by 45. It will be 0.1, isn't it? So 4.5 divided by 45 will be 0.1, 0.1. And there is a kilo 10 to the power 3 in the denominator. So in numerator will be it will be 10 to the power minus 3 again. So 0.1 milliampere. Now your output current in this case will be IF F plus IL, so 0.1 milliampere plus 0.9 milliampere. This will give you 1 milliampere. Your I naught, your output current, amount of output current will be 1 ampere. Now the next problem is, what changes should be made in the circuit so that the output current is doubled? Okay, so we need to double the output current. Doubling output current means your I naught has to be double of this, means 2 milliampere. Your I naught has to be 2 milliampere. Okay, now it also said here further that without changing the gain of the amplifier. So the gain of the amplifier is, your amplifier is minus of RF on RI. So here you see that you are not allowed to, without changing the gain of the amplifier means you are not allowed to change RI and RF value. Okay, you are not allowed to change your RI and RF value. So if you are not allowed to change your RI and IF value, that means your IF value cannot be changed. So you are not allowed to change 45 kilo ohm nor the 10 kilo ohm input resistance there. Here, if you are not allowed to change all these things, then that means RF and RI must be fixed, or your IF is fixed. Your IF has to be 0.1 milliampere. Yeah. So while fixing IF to be 0.1 milliampere, if you still want to double your I naught here, that is, if the I naught has to be 2 milliampere and your IF has to be 0.1 milliampere, your new IL value, the new IL value has to be 2 milliampere minus 0.1 milliampere. That will be your 1.9 milliampere. Okay, your load current value has to be 1.9 milliampere. So if for your load current to be 1.9 milliampere, and you know that from this relation here, your V naught is load current into load resistance, isn't it, RL? So your load current has to be 1.9 milliampere, means the new RL value has to be, V naught was minus of, V naught was, never mind about this negative and all, this is V naught is 4.5 volt. Your IL, the desired value of IL has to be 1.9 milliampere, 1.9 milliampere. So if you divide 4.5 with 1.9, 4.5 division with 1.9, this is going to be 2.368. Milli means 10 to the power